At the far edge of the heliosphere, where the breath of the sun thins into the wider medium between stars, survey instruments carry out their quiet routine. Arrays that never sleep watch for minor variations in charged particles, dust density, and faint points of light that drift across repeated frames. In those records, one entry appears at first as almost nothing, a barely significant rise in brightness against a background that seems unchanged. It is filed as an interstellar candidate, tagged by automated software and confirmed later by careful human eyes, a possible visitor moving inward from the dark between systems. The object is faint and slow in those early records, traced only as a sequence of coordinates and times. The logs from different observatories agree on its existence, yet somewhere inside that agreement a thin discrepancy begins. When the first timestamps are compared across agencies, some frames appear to share identical start times, even though the telescopes occupy distant longitudes and follow distinct scheduling patterns. The differences are tiny, buried in fractions of a second, but the coincidence is too neat. Observation windows that should be staggered by practical constraints instead line up in a way that makes the object present in more eyes at once than chance alone would normally allow. The data teams note this as an oddity. Timekeeping is complicated at the edge of the heliosphere. Signals from deep spacecraft must pass through noisy plasma, through shifting fields, through layers of relays and ground stations before they settle into databases. A small misalignment in timestamps is not unusual. Yet as more detections accumulate, the pattern remains. Independent networks from the International Asteroid Warning Network to smaller regional surveys report observations that cluster more tightly in time whenever the object grows slightly brighter or shifts its measured velocity. In the early weeks, the visitor is still little more than a set of numbers and angles. Analysts at the Minor Planet Center treat it as they would any new entry from beyond the planetary region. They compute a preliminary orbit check for potential risks to Earth and circulate updates through the Planetary Defense Coordination Office. Everything appears conventional. The path is hyperbolic, consistent with an origin outside the solar system. The measured brightness fits within expectations for an icy body of moderate size. There is no cause for alarm and no reason to suspect anything beyond routine celestial mechanics. Yet the timing irregularities persist. Deep space communication dishes tuned primarily to distant probes notice that their noise floor shifts slightly whenever the survey systems capture the object. The change is subtle, a small smoothing of background static, as though some part of the random hiss has been damped. Engineering teams attribute it to calibration cycles or seasonal conditions in Earth's atmosphere. Logs are annotated, tests are run, and the data are accepted with quiet footnotes that mark them as low-priority anomalies. Meanwhile, at the outer boundary where the solar wind slows and bends, a handful of spacecraft continue their slow passage. Their magnetometers listen to the structure of the heliospheric frontier, mapping the currents and shock fronts that shape the sun's extended environment. In their measurements, too, something begins to appear. When the trajectory of the interstellar candidate is projected outward, it crosses the regions these craft now inhabit. Shortly before each passage, the recorded field strengths fluctuate with a gentle, steady rhythm. The pattern is not dramatic, not the sharp spike of a flare or the jolt of a shock wave, but a mild and coherent variation that rises and falls like a quiet tide inside the data. The first detection teams treat these coincidences cautiously. The heliosphere is a restless place. Charged particles flow along magnetic lines. Shock waves ripple and turbulence stirs layers of plasma over vast distances. Still, the overlap between the predicted track of the object and the timing of the field variations draws quiet interest. Plots are made showing the approach of the visitor against the strength of the fluctuations, and the two curves glide past each other with a grace that feels more deliberate than random. At this stage, no rule is broken in any obvious way. Particles follow known laws, light travels as expected, and the object continues along a path that can be fitted with standard gravitational models. The mystery lies not in any single impossible event, but in the quiet coherence that seems to grow around the data set itself. Small mismatches in clocks, synchronized observation windows, and gentle field variations near the boundary of the heliosphere all remain within the limits of normal physics, yet together they form a pattern that resists easy dismissal. As more observatories tune their sensors toward the trajectory, scheduling their scans and exposures to catch the interstellar visitor on its way inward, that coherence slowly deepens. The surveys are designed to be independent, separated by geography and mandate, yet they begin to behave like parts of a single loosely coordinated network. Each time the object crosses a new threshold of brightness or distance, instruments that were built without knowledge of one another seem to act in a way that maximizes their shared coverage. In the language of official reports, none of this yet warrants special classification. The entry remains an interstellar candidate under routine monitoring, but the subtle alignments at the edge of the heliosphere, written in plasma waves, clock ticks, and survey schedules, form the first hint that the arrival of the object may not simply be a matter of a body passing through space. It may instead be the start of a condition that gathers itself quietly inside the systems built to watch the sky. At the center of the monitoring effort, the networks that watch the sky begin to turn their attention inward. Survey telescopes that once swept slowly across fixed grids now carve thin arcs that intersect a single moving point. Scheduling software reshapes its priorities, nudging exposure windows and repositioning instruments so that the interstellar visitor appears in frame more often than any ordinary comet or asteroid. None of this is intentional design. Each facility follows its own rules and obligations to catalog, safeguard, and report. Yet when their logs are stacked together, the pattern looks almost choreographed. The International Asteroid Warning Network refines its watch lists to include the newcomer. Requests move between observatories on mountain summits, desert plateaus, and high latitudes where the air sits thin and dry. Teams at the Minor Planet Center consolidate these reports with data from smaller arrays that contribute images from quieter corners of the world. Radio dishes that usually reserve their time for distant probes allow short intervals to track the object's changing position against the background of stars. Gradually, a distributed structure takes shape, a loose lattice of watchers that encircles Earth and reaches outward into space. Within this lattice, the object becomes more than a faint intruder at the edge of the heliosphere. It turns into a common reference point, a shared target that links instruments separated by oceans and languages. Observatories that rarely share schedules begin to align their tracking campaigns. One facility hands the object off to another as Earth turns, maintaining an almost continuous chain of coverage. Timekeeping systems that rely on atomic standards and satellite signals hold this choreography together, stamping each exposure with precise moments measured against universal time. In this phase, the data are still ordinary in appearance. Light curves drift upward as the visitor approaches, shaped by geometry and distance. Spectral lines are weak, but detectable, hinting at a surface that reflects less than most known comets. The coma, the thin envelope of gas and dust that surrounds an active body, remains faint. Nothing in the raw measurements forces a revision of physics. Yet within the metadata in the surrounding structure of when and how the measurements are taken, the first signs of deeper coordination begin to appear. Scheduling logs show that instruments separated by thousands of kilometers often adjust their exposure times within minutes of one another to accommodate follow-up observations. These shifts are subtle, sometimes no more than a slight lengthening of an imaging run or a delayed calibration cycle, but they recur around the same phases of the object's motion. Engineering teams explain these adjustments as reasonable responses to fresh information and updated predictions. New orbit solutions distributed through alert networks justify extended looks and altered plans. Still, the timing of the responses forms clusters that seem tighter than simple reaction. The Deep Space Communication Network joins this quiet convergence. Antennas that speak with spacecraft near Mars, Jupiter, and more distant regions schedule brief listening intervals toward the region of sky where the interstellar object travels. The main purpose is to refine its position and test whether any unexpected radio emission accompanies its passage. At first, nothing unusual is detected. The visitor remains a silent point, brightening slowly in reflected sunlight and leaving the radio spectrum empty. Even so, these pointed checks add another layer to the growing mesh of attention. Over weeks, a map of the network's behavior could be drawn not on the surface of Earth, but in time. Lines of observation overlap in bands where many systems act together. Gaps shrink as handoffs grow smoother. The interstellar visitor, still distant and quiet, now touches schedules for optical surveys, radio arrays, and plasma monitors. It does so without intent of its own that anyone can yet prove, but its presence calls forth an increasingly unified response from the instruments built to measure the sky. Formal reports remain measured, describing the visitor as a routine interstellar body and noting only that interest in it is unusually sustained across many facilities. Yet a secondary conversation begins to grow in informal exchanges. Some analysts remark on how often independent instruments seem to observe the visitor at nearly the same times. Others point to the unusual consistency in timekeeping records where corrections that usually scatter around small offsets now gather close to the moments when observations are made. These remarks are not yet formal findings. They drift like quiet currents beneath the mainstream of published results noted and set aside for later study. As the object moves inward and brightens, the network of eyes that tracks it settles into a new normal. What began as a scattered set of surveys has become a loosely coupled system holding the visitor within almost continuous scrutiny. The coordination remains explainable through established procedures and communication channels, yet the overall effect is one of increasing unity. From space and ground, from optical glass and radio steel, the instruments of many nations begin to act together as if they are parts of a single observing organism. In the numbers themselves, the interstellar visitor still behaves like a natural body following the pull of gravity. In the patterns that surround those numbers, another story is slowly forming. Every refinement in orbit, every adjustment in schedule, every shared timestamp tightens the weave of attention, without anyone deciding it should be, so the object becomes the center of a planetary experiment, one in which the experimenters do not yet realize how carefully they have arranged their own gaze. As the visitor glides inward and crosses the paths of the outer planets, quiet messages move through control rooms. Spacecraft that were never designed to study interstellar bodies are asked to turn. One of them, a patient orbiter circling Mars, receives updated pointing commands. Its cameras tuned for landscapes of dust and layered rock now strain toward a faint target against the deep background. Engineers adjust tracking software that once assumed slow-moving surfaces and fixed horizons. Now those same systems must follow a compact speck that drifts across the stars with steady speed. The first attempts are imperfect. Frames arrive in which the object appears as a blurred mark, streaked by motion and softened by the limits of guidance. Image processing teams refine their methods, building new filters and motion models almost in real time. They stack exposures, subtract noise, and align fields of stars, until the faint trace of the visitor begins to stand out. A space-based observatory that usually watches distant galaxies tilts by a small angle to capture short sequences, and a solar monitoring platform adds narrow windows between its regular views of the star. Gradually, the first clear portrait emerges. On screens in quiet labs, the interstellar body resolves into a tight, softly glowing sphere wrapped in a thin halo. The nucleus is too small to see directly buried within the surrounding light, but the structure of the halo is unmistakable. It is smoother than that of ordinary comets, lacking the obvious jets and knots that usually betray vents of gas and dust. The coma extends outward for thousands of kilometers, yet its brightness falls off gently and evenly, as though the material is being released in a controlled way. Ground-based telescopes operating at the limits of atmospheric clarity confirm the same pattern. Long exposures sharpened by adaptive optics reveal a shape that is almost perfectly round. There are no ragged plumes, no asymmetric fans, no bright spikes along the sunward side that would normally indicate violent outgassing. Photometric profiles show that the glow is slightly brighter near the center but remains remarkably symmetric. The visitor appears less like a crumbling snowball and more like a small, dark stone wrapped in a steady mist. In research institutes, expectations built from decades of comet studies begin to bend. Under the growing warmth of the sun, a body of ice and dust should boil unevenly. Patches of volatile material on its surface should respond to sunlight at different rates, carving channels and releasing bursts of gas that form distinct beams. That activity should translate into complex structure within the coma and into a visible tail stretching away from the star. Instead, the images show order and softness, a calm distribution of material that seems to contradict the usual behavior of fragile nuclei. Spectral studies deepen the unease. The halo's light carries signatures of material that appears darker and more metallic than expected, with only a thin contribution from familiar volatile ices. The visitor seems to possess a dense interior and a modest outer layer of lighter compounds. Such a body should favor sharp localized vents, yet every frame shows only a gentle and uniform sheath. Composition and appearance lean in different directions and refuse to meet. At the same time, dynamical models based on tracking data indicate that the object is already experiencing a small but measurable acceleration that cannot be accounted for by gravity alone. The effect resembles what outgassing would produce, a subtle push as material leaves the surface. The magnitude of this non-gravitational force suggests that a significant amount of mass is being lost. If that were true, the coma should not only be smooth and bright, but also should feed a clear extended tail reaching far into space. Yet the images from multiple platforms show no such structure. Observers search the space behind the object in the direction opposite the sun, where radiation pressure would normally herd tiny particles into a narrow luminous stream. Deep stacks of images combined over many hours of exposure are examined for any trace of a trailing feature. The results are consistently negative. There is no obvious tail, no faint ribbon, not even the thin spike of an ion stream at the sensitivity levels available. The visitor presents itself to every camera as an isolated sphere of muted light surrounded by a halo that ends abruptly rather than fading into a distant plume. This absence does not immediately overturn theory, but it presses against its boundaries. It suggests that if mass is being lost, it may be leaving in a form that does not scatter visible light in the usual way, or in paths that escape the cameras before a tail can gather. Ideas about fine hot particles and guided charged flows begin to circulate, but all remain tentative, sketched in preliminary notes and quiet discussions rather than announced as firm conclusions. Within the calm glow of the images, the interstellar visitor holds its silence. It offers no obvious sign of fragmentation or violent upheaval. The halo that surrounds it remains steady and symmetrical across many rotations and observation campaigns. For the network of eyes that now watches almost without pause, this steadiness is both reassuring and disquieting. Nothing appears to be breaking apart, yet something unseen seems to be happening with great efficiency. The first clear portrait has been taken, and it shows a body that obeys the broad outlines of cometary physics, while quietly ignoring some of its most familiar signatures. Orbit fitting is a careful craft, a weaving of numbers into a path through space. As the interstellar visitor continues inward, the observational arc grows longer, and with it the precision of its predicted track. Teams at planetary defense centers, university observatories, and space agencies feed new positions into shared models. Each measurement adds a point to an invisible curve, refining where the object has been and where it will go. At first, the fits are well behaved. The hyperbolic path aligns with expectations for a body arriving from beyond the solar system, guided by the combined gravity of the sun and the planets. Uncertainties shrink as more data arrive, and the projections for future positions narrow into smooth corridors of likelihood. Alerts confirm that there is no threat of impact with any major world. The visitor is cataloged and quietly folded into routine tracking bulletins. Then slowly the neatness begins to fray. Residuals, the differences between observed positions and calculated ones, stop shrinking in the way they should. Instead of random scatter, they begin to drift in a persistent direction as though the object is being nudged along its path. The effect is minute, buried inside tiny angular offsets, but it refuses to vanish when models are updated. The body is moving slightly faster away from the sun than gravity alone can explain. Many comets experience non-gravitational acceleration when warmed surfaces release gas. Analysts know how to include such forces using standard terms that tie outgassing to the curve of motion. They introduce those terms into the models for the interstellar visitor, expecting the residuals to flatten once more into noise. Instead, a different picture emerges. When the extra component is fitted, it comes out both stronger and more orderly than anticipated. The added acceleration points almost directly away from the sun, with only a modest sideways part along the orbit. Its magnitude suggests that a great amount of mass is leaving the body, far more than the faint coma would imply. Even more striking is its steadiness. Over many weeks, as the object approaches and passes its closest distance, the extra push varies only gently, following a smooth curve that seems almost designed. In internal notes, some orbit specialists describe the effect as too clean. A natural jet driven by patchy ice should flicker as rotation brings different areas into light and shadow. The force on the nucleus should wobble, strengthening and weakening as vents turn and fade. Here, by contrast, the added acceleration grows as the sun's heat increases, peaks near the expected point and declines again, but it does so with a symmetry that leaves little room for random geography. The absence of visible exhaust deepens the puzzle. If billions of tons of material are being lost, they do not appear as bright dust or extended gas structures. There is no broad tail arching away into darkness, no fan of debris to match the inferred flow of momentum. Infrared telescopes look for warm grains, while ultraviolet instruments hunt for faint ion trails. All return only the same modest halo, smooth and compact around the nucleus, with no sign of the kind of mass flux that the orbit solutions demand. Some teams consider whether the acceleration might be an artifact of data handling. They test for biases in star catalogs, atmospheric distortions, and timing errors. They simulate the effects of imperfect tracking and misaligned reference frames. Each idea is examined and compared to the residuals. None reproduces the subtle, persistent push that the observations reveal. As results are shared between institutions, a consensus forms that the non-gravitational terms are real. The interstellar visitor is indeed experiencing a gentle but sustained thrust. In formal reports, this is described cautiously as outgassing from a body with unusual composition and geometry. Yet in more candid exchanges, the language sometimes shifts. Researchers speak of a thrust curve and of a controlled release. The words do not claim intention, but they carry the impression of a process that behaves less like random venting and more like a regulated system. To preserve balance, alternative explanations are developed in parallel. Perhaps the mass that leaves the surface is exceedingly fine, converted into plasma that couples efficiently to the solar wind and disperses before it can form a tail. Perhaps the structure of the nucleus channels gas through deep fractures, smoothing out fluctuations that would otherwise break the symmetry. In computer models, complex shapes and temperature patterns are tested, seeking a natural configuration that would generate a steady sunward-aligned force without producing visible debris. None matches all aspects of the data at once. Throughout this process, the visitor continues on its way, indifferent to the effort spent on understanding it. It does not flare dramatically or tumble into fragments. It maintains its calm halo and its dark interior, letting its motion through space carry the record of what is happening beneath the light. The orbit plots on analyst screens, once simple arcs, now appear with slight but undeniable deviations, like the path of a vessel making long, slow adjustments rather than coasting freely. In this silent change of motion, the interstellar object begins to move from being merely a body into being a behavior. Its physical form remains distant and unresolved, but its acceleration has become a measurable story. Gravity writes one line and the object writes another just beside it, using a force whose source refuses to show itself. Between those two lines, a quiet hint appears that whatever is unfolding may not be confined to matter alone, but may already involve patterns of energy and flow that reveal themselves only through the way the visitor chooses to move. As the interstellar visitor draws closer to the inner system, a new layer of observation begins. Thermal instruments tuned to measure how surfaces absorb and release energy are brought into coordinated use. These systems operate across long wavelengths that reveal heat rather than light, offering a view of the object that optical cameras cannot provide. Ground observatories equipped with infrared mirrors schedule longer exposures. Spacecraft trailing Earth widen their scan patterns to capture the visitor on approach. Even solar monitoring platforms add auxiliary checks, measuring the infrared sky near their regular fields. In the earliest thermal maps, the visitor is barely more than a smudge faint against the background glow of zodiacal dust. Analysts adjust their expectations accordingly. An object so small and dark is not expected to radiate strongly until it nears the warmth of the sun. Yet, as the object moves inside the orbit of Mars, the faint smudge sharpens into something unexpected. Instead of a smooth rise in temperature across its sunlit hemisphere, the heat signature arranges itself into a pattern of contrast. One region, near the subsolar point, appears cooler than predicted, while a band along the trailing edge remains consistently warmer regardless of rotation. Thermal inertia could explain part of this effect. Different materials release heat at different rates, but the pattern holds even when models account for rotation period, surface roughness, and possible metallic content. The cold patch follows the sun-facing side too precisely, as if the heat is being redistributed before it can accumulate. The warm band, meanwhile, retains its temperature through periods when it should cool rapidly. It behaves almost like a channel of steady energy, conducting heat along a path that does not match the simple geometry of sunlight. Infrared teams compare notes. At first, each group assumes an error in calibration. Thermal readings across different instruments are prone to drift, and detectors require constant correction. But as the data are exchanged, a convergence becomes clear. Observatories in Chile, Hawaii, and the Canary Islands show the same asymmetric thermal structure. Instruments aboard spacecraft corroborate it from different angles. A distinct cool zone and a persistent warm band trace across the visitor's surface in ways that no single instrument or atmospheric condition could mimic. This discovery leads to a question that grows quietly within analysis teams. If the visitor is losing mass at a steady rate driven by solar heating, why do the thermal signatures not reflect ordinary sublimation? Gas escaping from volatile deposits should leave hot streaks where sunlight strikes deepest, creating bright thermal jets. Instead, no such jets appear. The halo remains smooth and the surface temperature avoids sharp spikes. The heat seems to travel and settle along invisible routes as though being guided. Research groups attempt to explain the behavior with natural mechanisms. One hypothesis suggests that the interior of the nucleus might contain layered materials with extreme conductivity, transferring heat through narrow veins before releasing it into surrounding gas. Another proposes that the visitor's rotation might be influenced by pockets of dense metal altering how heat spreads across the surface. Models based on these ideas are run repeatedly, tuned and refined. They reproduce fragments of the observed pattern but never the whole. As thermal readings grow clearer, a second phenomenon emerges. The visitor's heat signature appears to fluctuate in sync with minor variations in the solar wind. When streams of charged particles intensify around the sun, the warm band brightens by a small but measurable margin. This correlation remains faint and requires long averaging to detect, but it persists across multiple passes. The object's surface seems to respond not only to sunlight but also to the shifting patterns of magnetic and charged flows that emanate from the star. This observation leads some analysts to explore more speculative ideas. Plasma physics allows for the possibility that fine charged dust or metallic grains could interact with solar wind pressure, creating localized heating or cooling zones. Perhaps the visitor carries a mantle of conductive material that channels energy along paths shaped by the interplanetary magnetic field. Such interpretations remain grounded in known science, yet they feel stretched, reaching beyond the usual conditions experienced by small bodies. In the calm rooms where data are reviewed late into the night, the thermal maps are studied with increasing attention. They reveal a surface that neither behaves like porous ice nor like solid metal, but something that straddles both extremes. It appears resistant to overheating, yet capable of holding warmth long after it should dissipate. Its patterns are too stable to be random, too subtle to be mechanical, and too consistent to be ignored. Through all of this, the visitor maintains its steady pace. Its halo glows with quiet symmetry, and its path continues to show the same gentle deviations first detected weeks earlier. The thermal divergence becomes one more signature layered onto a growing list of behaviors that hint at a coherent system, rather than an accidental assemblage of rock and ice. By now, the interstellar visitor has crossed a threshold. It is no longer interpreted solely through its visible form. Instead, it reveals itself as a pattern of interactions between light and heat, between solar wind and surface, between motion and energy. In the deepening record, the behavior seems less like the simple response of a passive object and more like the unfolding of an internal process. A process that remains unseen but expresses itself through every map curve and measurement gathered so far. As the visitor approaches the region where the sun's magnetic influence twists into a broad wavering sheet, the network of sensors that listens to the heliosphere enters a period of sharper vigilance. The heliospheric current sheet, a vast structure shaped by the slow rotation of the star, forms a rippled boundary between magnetic polarities. Charged particles drift along it, radio waves bend through it, and spacecraft pass through its folds with careful monitoring. It is not a place marked by abrupt changes, but by gentle gradients that stretch across millions of kilometers. When the interstellar object draws near this boundary, magnetometer arrays distributed across Earth and throughout the solar system begin to show a pattern. The measurements rise and fall with unusual coherence, forming a sequence of small waves that seem to move ahead of the object's projected path. These fluctuations are not violent. They appear as slight rotations in field direction, small increases in field strength, and delicate shifts in the frequency of background magnetic noise. Each variation is subtle enough to escape notice on its own, but when the data from many stations are combined, the pattern is unmistakable. A faint signature seems to travel through the current sheet as the visitor approaches, as though its passage rearranges the magnetic landscape before it arrives. Monitoring teams review the data. They run comparisons against solar wind conditions, searching for connections to coronal holes or minor eruptions that might produce similar patterns. They test for instrumental drift and background variations caused by Earth's own magnetic environment. Yet the timing of the fluctuations lines up most closely with the object's motion. When the visitor is far, the signature is absent. When it draws close to the current sheet, the pattern grows. As it crosses, the variations reach their peak and then recede in a slow, graceful decline. Spacecraft positioned near Mars and Venus confirm these findings. Their instruments detect slight ripples in magnetic field strength that match the timing recorded near Earth. The ripples travel outward along lines shaped by the current sheet, moving from region to region as if tracing the visitor's projected path. Even distant probes in the outer heliosphere register small coordinated disturbances that appear to reflect the visitor's movement rather than any solar event. The effect forms a broad arc across the system, linking sensors separated by immense distances. These observations prompt new discussions among researchers. One idea suggests that the visitor carries a significant magnetic moment of its own, perhaps generated by a metallic interior or by charged dust streaming from its surface. Yet no strong magnetic field is detected directly. Instead, the signals imply a softer presence, an influence that shapes the flow of charged particles without revealing a clear source. Some compare the behavior to the passage of certain plasma structures, objects, or clouds that do not radiate much energy but leave trails of ordered motion in the fields they cross. A different idea emerges from teams studying solar wind models. They note that the visitor's gently accelerating motion could reshape the charged environment around it in ways that mimic a magnetic interaction. The slow, steady release of material, if ionized, might couple to the solar wind, creating a long, invisible sheath of altered plasma. This sheath could drift along with the object, carrying small disturbances outward into the heliospheric current sheet. But calculations suggest that the required mass flow would be larger than what observations reveal, unless the escaping particles are extraordinarily fine and disperse with unusual efficiency. Through quiet exchanges, another thought begins to circulate. The coherence of the fluctuation seems greater than that produced by simple plasma flow. The signals appear to travel ahead of the visitor, not merely trail behind it. They suggest an interaction that reaches into the structure of the heliospheric field, touching the boundary before the object arrives. Some speculate that the visitor may be responding not only to local conditions, but to the broader shape of the Sun's magnetic architecture, adjusting its behavior as it approaches regions of complex polarity. These ideas remain cautious and grounded. No one claims an exotic mechanism, yet the convergence of evidence thermal patterns that seem to follow solar wind changes non-gravitational motion that remains too smooth, and magnetic variations that move in step with the visitor raises a quiet curiosity. It is as though the object is more sensitive to the heliosphere than any comet known, almost as if it reads the magnetic terrain and interacts with it in a way that is subtle but systematic. Meanwhile, the visitor crosses the current sheet. Its halo remains calm. Its trajectory shows the same gentle deviations seen earlier, neither chaotic nor abrupt. The magnetic fluctuations reach their peak and then spread outward, fading into the background noise as the object moves beyond the boundary. At global monitoring centers, plots show the disturbances lengthening into soft curves that mirror the visitor's passage like ripples in a layered pond. As the data are archived, the event is recorded with measured language, a coordinated set of field variations consistent with passage through a dynamic region. Yet many who studied the event carry with them a quieter impression that the visitor's transit through the current sheet behaved less like an object disturbing its environment and more like a process unfolding within it. The boundary reacted, the field shifted, and the visitor moved through the changing geometry in a way that seemed both natural and strangely aligned. This moment does not provide answers, but it marks a turning point. For the first time, the interstellar visitor appears not only as a physical body, but as something that interacts with the solar system on multiple levels: light, heat, motion, and now magnetic field. The heliosphere itself becomes part of the observational record, shaped and stirred by an object that remains quiet and distant, yet increasingly complex in the patterns it leaves behind. Long before the visitor reaches its closest point to the Sun, another pattern begins to surface, one not written in heat or motion, but in the behavior of the machines that record its passage. These systems spread across observatories, relay stations, and data centers are built to preserve information faithfully. Each exposure, each telemetry packet, and each spectrum is stored through redundant layers of hardware and software designed to prevent loss. They operate in different countries under different agencies using different storage architectures, yet as more data accumulate, threads of an unfamiliar consistency begin to appear. It starts with a few corrupted frames. A series of images from a desert observatory arrive with missing segments, thin rectangles of silence where stars should be visible. The gaps are small enough to blame on transmission noise, though the weather was calm and the network stable. A week later, a spacecraft sends a burst of spectral data containing several empty lines, blank regions where the detectors had been active only minutes before. Engineers attribute this to a transient fault in the onboard memory, but the problem does not repeat when the instrument retakes the same measurements. In another facility, 2 calibrated exposures from a high-altitude telescope fail to save properly. When recovered from the storage logs, the timestamps remain intact, but the image arrays are partially overwritten with uniform values as though a smoothing function had passed across them. The issue is logged as unusual but not unheard of. Even modern systems experience rare faults. But then similar irregularities are found in archives on a different continent involving unrelated equipment operating under different protocols. Initially, no one connects these events. Data anomalies are common in astronomy. Cosmic rays strike detectors, storage clusters undergo silent bit flips, and compression algorithms occasionally falter. Yet as the visitor moves deeper into the inner solar system, these small events occur more frequently and with a subtle but recognizable rhythm. The corrupted intervals cluster around the same spans of time when the object crosses certain regions of space, or when its light grows momentarily brighter. The patterns are still faint, hidden inside thousands of hours of clean data, but they persist when reanalyzed. Teams begin to exchange notes. A quiet question emerges in long email threads and late evening calls. Why are the gaps so consistently aligned with key phases of the visitor's activity? When data sets are compared, the missing patches form a loose, wave-like sequence through the global archive. No single system records all the gaps, but together they sketch an outline as though information is being gently removed, never dramatically, never in ways that jeopardize safety or mission integrity, but enough to soften specific details. The simplest explanation is that these events coincide with periods when instrumentation is stressed by rapid changes in brightness or pointing. This is plausible for some anomalies, yet others appear during calm intervals when neither the sun nor the visitor changes significantly. Efforts to blame network congestion or software updates fail to match the timing. Some artifacts occur in locations without active maintenance, others in deep space systems isolated from Earth's patterns. The emerging picture is subtle. The visitor does nothing overt. It emits no radio noise, no detectable interference, and no measurable field capable of corrupting memory. Yet the gaps spread across instruments as though they are part of a larger distributed phenomenon, pieces missing from different corners of a puzzle, removed in a way that avoids drawing attention. Researchers entertain more natural explanations. Perhaps the fine material escaping the visitor carries enough charge to interact with detectors in low Earth orbit, increasing noise. Perhaps minuscule solar wind fluctuations triggered by the visitor's passage create conditions that amplify bit errors. These ideas remain grounded, sensible, and testable, but none fully account for the coordination of the missing data across systems that share no physical connection. Some analysts describe the effect with careful understatement. The data do not appear lost. They appear absent, as if they were never recorded, or as if the instruments looked and found something their architectures were not built to store. The phrasing is metaphorical, not literal. No one suggests an active removal. Yet the sensation remains that the archive is being shaped, not broken. That the missing parts are not random failures, but quiet omissions aligned with the visitor's pattern. As the object moves inward, these small gaps accumulate. They do not compromise scientific work. Enough clean data remain for models to run, for trajectories to update, for spectra to be analyzed. The science progresses. But behind the clean graphs and neat plots lies an undercurrent of uncertainty. The maps of missing information drift like shadows beneath the main results, hinting at a structure that touches the very systems built to observe. By now, the visitor is not only a source of light and heat, but also a subtle presence in the digital fabric that records the universe. Its passage generates not only fields and motion, but also faint patterns of absence that spread across storage logs and instrument archives. It shares no message, no signal, no trace that can be decoded. Instead, it leaves the suggestion of a process that brushes lightly against memory itself, as though the phenomenon surrounding the visitor extends into the systems tasked with capturing its story. As the visitor rounds its slow inward arc toward the sunlight, becomes the primary medium through which its behavior is known. Optical and ultraviolet surveys tighten their cadence, gathering images at intervals measured in minutes rather than hours. Spectral instruments monitor subtle changes in color and line intensity. The global network of observatories now operating in an almost seamless relay prepares for the brightening that inevitably accompanies a body nearing perihelion. Yet when the increase in luminosity arrives, it does so in a way that no model predicts. Instead of a dusty flare or a chaotic bloom of vapor, the visitor brightens in a single smooth shift. The event spans only a short interval, not sharp enough to be called instantaneous, yet not gradual enough to be explained by normal sublimation. Light curves from multiple observatories rise in perfect alignment, forming a clean, uninterrupted step. The brightness multiplies several times, pushing the halo into a colder, bluer spectrum. The blue tone is the first surprise. Comets typically brighten in warm hues, a mix of scattered sunlight and emission from heated dust. Their glow carries a signature of ice and silicate grains softened by sunlight. Here the light is crisp metallic and faintly ionized, as though the halo has shifted into a different physical state. Spectral lines show hints of plasma activity, though of a kind too cool and too uniform to match known cometary processes. In images returned from spaceborne cameras, the halo does not swell outward as would be expected from a sudden release of gas. It retains its shape, smooth, symmetric, and faintly layered, as though the brightening came not from new material, but from a change in the state of material already present. Observers who compare frames before and after the pulse note no new structure, no jets, no fragmentation, only the intensity has changed. The most striking feature is the stability that follows. Over the next several weeks, the visitor maintains its new level of brightness with uncanny steadiness. There are no fluctuations, no flickers, no variations driven by rotation or solar wind conditions. The halo emits at a constant intensity, like a lamp held at a fixed setting, even when the solar wind briefly intensifies, carrying streams of charged particles past the object the light holds unchanged. In standard comet behavior, such disturbances would create ripples of brightness or shifts in the orientation of the halo. Here nothing of the kind appears. In deep review rooms, scientists gather to study the light curves. They note the remarkable precision of the rise. The increase spans nearly the same duration in all datasets, regardless of the observing angle. This uniformity suggests that the brightening originates from a process distributed evenly around the nucleus, a mechanism more global than local, affecting the object as a whole rather than any single region. Theories form cautiously. One possibility is that the visitor's surface or halo contains fine metallic grains capable of entering a brief, self-sustained ionized state. Under the right combination of temperature and solar wind, such grains might emit uniform light without significant mass loss. Another idea proposes a plasma sheath surrounding the nucleus, a thin layer of charged material that can shift into a more luminous mode under solar influence. These ideas remain grounded in known physics, yet they stretch conventional boundaries. The visitor's brightness does not fade quickly, nor does it intensify. It holds steady for more than 2 months, suggesting a regulated state rather than a transient effect. The calmness of the glow makes the brightening resemble less a flare and more a transition, one phase of behavior giving way to another. Photometric models that attempt to capture the event run into a peculiar difficulty. To match the observed stability, the energy input from the sun would need to be redistributed evenly across the surface or the halo. But the thermal maps show no such symmetry. The warm band and cool zone persist through the brightening, behaving independently of the optical change. Heat and light seem to belong to different processes unfolding in parallel. A more speculative line of thought suggests that the object may be reacting to the solar environment not only in terms of temperature but also in terms of electromagnetic structure. The shift in brightness could reflect a change in how the visitor interacts with the heliospheric field, perhaps a reconfiguration within the thin envelope surrounding it. No evidence confirms this yet, but the idea settles quietly into analytical discussions carried forward by the way the halo glows with uniform, controlled energy. Throughout this period, the object remains serene. It does not outburst or fragment. It does not produce the turbulence that accompanies intense sublimation. Its halo holds its shape, its motion stays smooth, and its constant brightness accompanies it like a silent signature. In the archives, the brightening is recorded as an optical transition event. The terminology is precise, neutral, and deliberately unassuming. Yet those who study the data often describe it in softer terms. They say the visitor seems to have entered a new state, a luminous mode that reveals not fragility but composure, as though the object adjusted its presence rather than reacted to stress. What remains most striking is not the brightness itself, but how quietly it unfolds. The interstellar visitor changes its light in a way that feels less like a flare and more like a decision expressed through a glow that stays steady in the shifting winds of the inner solar system. As the brightening settles into its long, steady plateau, attention turns again to the path the visitor carves through space. The orbit has been refined many times already, each new measurement folding back into models maintained at planetary defense centers and space agency dynamics teams. Now, with the object closer and its position easier to measure against dense star fields, the precision of those models improves further. Small uncertainties shrink and the predicted track narrows into a thin, elegant curve grazing the inner orbits. Yet, even within this heightened clarity, something quiet continues to slip away from expectation. The residuals that first hinted at non-gravitational forces do not dissolve under better data. Instead, they arrange themselves into a pattern of gentle drift. Observed positions arrive just outside the already adjusted predictions, not in random directions, but along a smooth bias that appears to evolve coherently over time. When plotted day after day, the differences form a line of their own, a faint track running beside the main orbit solution. To understand this behavior, dynamics specialists turn to more sensitive methods. In addition to optical astrometry, they incorporate timing from spacecraft occultations, moments when the visitor passes near the line of sight between Earth and distant probes. These subtle events alter signal paths by tiny amounts, allowing precise constraints on the object's position. Deep space communication antennas record slight variations in phase and delay that, when processed, refine the distance to the visitor beyond what sky angles alone can provide. With these new inputs, the models grow more intricate. Three-dimensional fits now include not only the standard gravitational parameters and a simple outgassing term, but also higher-order components tied to the object's orientation and rotation. The aim is to capture any plausible natural source for the measured drift. Simulations explore irregular shapes, tilted spin axes, and patchy thermal patterns. Each configuration generates a predicted non-gravitational force, which is then compared to the observed deviations. What emerges is a curve of acceleration that is both familiar and strange. Its overall shape resembles that of known cometary outgassing, rising as the object approaches the Sun, peaking around perihelion and falling away as it recedes. But within this envelope, the details differ. The acceleration is smoother, its direction remains tightly aligned with the radial and along-track axes, and its variability is lower than any model with realistic surface irregularities can produce. In ordinary comets, the thrust wobbles as vents rotate in and out of sunlight. Here the thrust appears regulated, as though fluctuations are damped before they can imprint on the orbit. Over weeks, this regulated force accumulates into a measurable change in trajectory. The visitor's path bends slightly away from close planetary encounters and shallowly adjusts its inclination, minimizing its time near dense regions of dust and debris. These changes are small in absolute terms, but large compared to what random outgassing patterns would normally achieve. When analysts project the path forward using only gravitational influences, the predicted curve diverges slowly from reality like a free drifting line separating from another that is being gently steered. This effect becomes most apparent when comparing early predictions with later reconstructions. Orbit solutions computed months before perihelion had placed the outbound leg of the trajectory on one side of a narrow spatial corridor. Updated solutions fitted after the sustained non-gravitational acceleration is fully accounted for now show the visitor exiting through a slightly different corridor, one that threads between planetary orbital nodes with greater clearance. It is as though over time the path has been trimmed to avoid certain alignments, not dramatically but with quiet precision. To maintain scientific discipline, analysts continue to search for purely natural explanations. They consider whether the visitor might possess internal reservoirs of volatile material buried beneath a hardened crust, releasing gas through deep fractures in ways that smooth out variations. They explore the possibility of phase changes within metallic or mineral components, transitions that could regulate the flow of gas as temperature passes through specific thresholds. Computational models test these scenarios under a wide range of assumptions, yet none fully reproduces the combination of steadiness, directionality, and accumulated orbital effect observed in the data. In parallel, orbital fits are carried out independently by multiple institutions. Centers at space agencies in different nations, along with university groups, perform their own analyses using distinct software suites and reference catalogs. The results converge. Despite differences in method, all teams report the same pattern of controlled drift. The visitor's motion resists reduction to a simple cometary analog. It behaves instead like an object following a plan written partly by gravity and partly by an unseen, softly regulated process. The mood among dynamics specialists is not one of alarm, but of deepened curiosity. They are accustomed to outliers, to objects whose paths demand more parameters or better measurements. Still, there is something about the coherence of this case that sets it apart. The visitor does not simply misbehave, it misbehaves consistently. Its deviations from prediction are not jagged or impulsive. They form a calm narrative of gradual adjustment, as if each small change in its motion relates to a larger pattern rather than to random surface events. Some discussions venture into more speculative territory while remaining anchored in restraint. A few researchers note that the pattern of drift resembles the effect of long-duration, low-intensity propulsion, such as that produced by certain electric or plasma engines aboard spacecraft. The analogy is imperfect and framed carefully, but it lingers, a steady directional push applied over long spans accumulating into meaningful course corrections. In the formal literature, this comparison is translated into cautious language about sustained, smooth, non-gravitational forces. Throughout these debates, the visitor continues its journey. It does not acknowledge the models built around it. Its halo remains stable, its brightness steady, its thermal features persistent. Only the changing curve of its path speaks to what unfolds at a deeper level. The orbit that once seemed fixed by its entrance conditions now appears as a canvas upon which another process has left delicate marks. By the time the object begins its gradual retreat from the Sun, the sense has taken hold that its trajectory tells a story beyond simple passage. It not only comes and goes, but adjusts how it does so in ways that appear optimized for a pattern no one has yet deciphered. Gravity provides the stage, but something within or around the visitor seems to be quietly directing its steps, trimming its course with a patience that stretches across months. Long before the visitor leaves the inner system behind the planets themselves, begin to register its passing in ways that are not captured by light alone. Magnetic observatories on Earth and in orbit watch the ceaseless dance of auroras, substorms, and ring currents that circle the globe. Similar monitors near Jupiter and Saturn track the vast fields that enclose their moons. These systems are accustomed to the Sun's moods, the arrival of coronal streams, the sweep of shocks, the gentle swells of background wind. Against this familiar backdrop, the influence of the interstellar body is at first almost imperceptible, a whisper within the larger song. On Earth, the network of ground-based magnetometers notices slight deviations in the nightly pattern of high-latitude currents. The changes are not strong enough to trigger alarms. They appear as small, coherent shifts in the timing of auroral brightenings and in the onset of substorms. When compared to records from many years, these deviations stand out only because they recur on nights when the visitor occupies particular regions of its orbit. The local time of auroral arcs drifts in step with the object's angular position relative to the planet, as though something in near space is quietly adjusting the rhythm of charged particles that fall into the upper atmosphere. Spacecraft within Earth's magnetosphere confirm subtle changes. Instruments that monitor the ring current, a wide band of charged particles encircling the globe, detect modest but synchronized enhancements. These enhancements occur not during major solar events, but during calm periods when the solar wind is steady and unremarkable. The added energy appears as a gentle thickening of the ring, a slight increase in particle density and average speed. The timing of these enhancements aligns more closely with the visitor's orbital progression than with any change in solar output. Similar patterns appear with their own distinctive signatures at other worlds. Near Jupiter, probes monitoring the immense magnetic field and its luminous auroras notice that certain recurring features shift their phase during the visitor's passage through the outer reaches of the system. The great planet's polar lights, usually governed by its rapid rotation and by interactions with its volcanic moon Io, show small phase drifts that correlate with the evolving position of the interstellar object. The changes are minute, buried within the more dominant dynamics of the Jovian environment, yet they are reproducible when the data are folded over the visitor's timeline. Researchers treat these findings with caution. Planetary magnetic environments are rich with internal cycles and resonances. It is natural for auroras and ring currents to vary under many influences, including factors not yet fully understood. Yet when the data from multiple worlds are compared, a quiet coherence emerges. The timing of the murmurs in each magnetosphere appears linked by geometry to the visitor's path, as though the object is moving through a web of invisible threads that connect planetary fields through the solar wind. To explore this possibility, teams construct models that trace how disturbances propagate along magnetic field lines and plasma flows. They simulate how a small but persistent change in the heliospheric current sheet, such as the ripples observed during the visitor's crossing, might feed into planetary environments. These models can explain some of the correlations, especially the idea that a global shift in the solar wind structure would alter energy input into multiple magnetospheres at once. However, the models typically predict broader, less synchronized effects than those actually recorded. The observed patterns are narrower in time, more sharply tied to specific orbital phases. A more nuanced view begins to take shape. Perhaps the visitor is not injecting raw energy into planetary fields, but is instead modulating the pathways along which energy already flows. In this picture, the object acts as a moving lens within the heliospheric plasma, subtly redirecting streams of charged particles and altering how they encounter the magnetic shields around planets. The visitor would not need to be powerful in an absolute sense. It would only need to interact with the surrounding medium in a way that shapes existing currents. Evidence for this view remains indirect. The visitor's halo shows no obvious extension toward any planet. It emits no distinct radio bursts tied to the magnetic disturbances. Yet the repeated alignment of auroral timing shifts, ring current enhancements, and the object's position suggest that the heliosphere is at least temporarily behaving as a coupled system with the visitor as one of its active nodes. The phenomenon feels less like a local effect and more like a condition that spreads along field lines and flows. Through it all, the planets continue their steady circuits. Their auroras shimmer, their magnetic shells flex, and their ring currents flow as they always have. The visitor moves among them without direct contact, never approaching close enough to pose any risk. Its influence, if that is what it is, manifests only as gentle adjustments at the edges of measurement, small shifts in phase amplitude and timing that would be easy to overlook without the concentrated attention now focused on this passage. In the measured language of official reports, these effects are described as correlated anomalies in planetary magnetospheric activity, potentially linked to transient restructuring of the solar wind. Behind that language lies a more quietly held thought that the interstellar object may be sampling or even shaping the magnetic envelopes of worlds as it passes, not by force, but by participating in the fields that already surround them, turning a single transit into a shared experiment written in the faint murmurs of planetary space. Even as the visitor threads its way among planetary fields, another form of coherence begins to surface, one woven not through particles or light, but through the infrastructure that spans Earth and its orbiting fleet. These systems, built to communicate with distant spacecraft, to synchronize clocks, and to coordinate global observation networks, operate with precision born of necessity. Their signals form the nervous system of planetary science. Under ordinary conditions, they whisper across continents and deep space with stability measured in billionths of a second. But during the weeks surrounding the visitor's closest approach to the Sun, this stability begins to quiver. At first, the changes reside deep in diagnostic logs. Several ground stations report slight irregularities in their timing references, not enough to affect operations, but notable because they appear at the same universal moments despite being on opposite sides of Earth. Corrections that normally scatter around small random offsets tighten into narrow clusters. The clocks do not drift apart, they drift together as though nudged by the same faint external pulse. Soon after, the Deep Space Communication Network records brief synchronized deviations in signal coherence. These are not dropouts or faults. Instead, they manifest as momentary smoothing of noise in certain frequency bands, similar to the subtle effects noticed months earlier at the edge of the heliosphere. Analysts expect such events during solar storms, but the solar wind is quiet during these intervals. There are no flares, no shocks, no significant variations in the ionosphere. Still, the pattern repeats a soft alignment of noise floors, timed to the visitor's evolving geometry. Relay satellites in high orbit experience something similar. Their diagnostic systems register short intervals in which error-correcting algorithms work less, not more. Bit error rates dip subtly below normal background levels as if the ambient static of space has been thinned. The events are too brief and too slight to trigger alarms, but when compared across multiple satellites, the timing aligns. The dips appear as small humps on long plots, coherent, gentle, transient. In fiber-linked observatories on the ground, the effects manifest as well. Atomic clocks that anchor timekeeping for large telescope arrays undergo rare but simultaneous micro-adjustments. These adjustments remain within expected precision but stand out because they occur in parallel across continents. In one instance, 3 arrays performing coordinated spectroscopy detect identical delays in their calibration pulses, delays so small they occupy only the margins of statistical noise, yet perfectly aligned in time. No system malfunctions, no data are lost. The infrastructure continues to operate as designed. But the consistency of the timing deviations becomes impossible to overlook once the data sets are layered together. Investigators explore natural explanations with meticulous caution. They consider the possibility of distributed ionospheric effects, global shifts in atmospheric density that change how signals propagate. But the timing of the anomalies does not match known atmospheric cycles. Next, they evaluate the idea of a subtle modulation in the cosmic ray background, perhaps influenced by the visitor's passage through the solar wind. Yet this too falls short. Cosmic ray levels fluctuate, but not with the tight synchronization observed. A third possibility is that the visitor's halo, now in an ionized state, might be interacting with the solar magnetic field in a way that produces coherent low-frequency oscillations throughout the heliosphere. Such oscillations could in principle alter the noise characteristics of communication links and the behavior of timing systems on a global scale. Models exploring this scenario produce only partial matches. Some frequencies align, others do not. The coherence remains stronger than the models predict. Quietly among technical discussions, a more philosophical question emerges. Are the networks responding to the visitor or merely synchronizing with a change in the solar environment that the visitor also reflects? If the latter is true, then the visitor is not the source, but a participant in a wider shift passing through the heliosphere. This idea offers comfort, for it keeps every element within natural bounds. Yet it fails to explain why the coherence grows strongest when the visitor occupies specific magnetic and gravitational positions relative to Earth. Some analysts describe the pattern in abstract terms. They say the infrastructure seems to lean toward alignment near certain phases, as though its clocks, frequencies, and error patterns drift minutely into resonance with an evolving condition in space. The phrasing avoids speculation, but the metaphor carries weight. The visitor is not altering signals, rather the signals appear to momentarily inhabit the same pattern of behavior, a faint shared rhythm passing through instruments built for precision. In the official record, these events are classified as minor timing and coherence anomalies of uncertain origin not affecting operations. That description is accurate and appropriately cautious. Yet for those who study the convergence across systems, radio links, calibration pulses, atomic clocks, relay satellites, the impression becomes difficult to shake. The visitor's presence is felt not through disruption but through synchronization. As if for brief intervals, instruments scattered across the planet and beyond fall into a gentle agreement shaped not by design but by participation in an unseen, slowly shifting pattern. A pattern that does not command but invites a quiet alignment written not in force but in timing. In the wake of these events, the infrastructure resumes its ordinary behavior, leaving behind only traces in logs and a lingering curiosity among those who examine them. Whatever passed through the networks left no damage, only the suggestion that the visitor's story is expanding beyond matter and motion, reaching softly into the systems humanity uses to measure the universe itself. As the visitor sweeps past the sun and begins its outward leg, telescopes expect it to dim, fragment, or fade into the long arc of its departure. Instead, something quieter and stranger unfolds. The visible body begins to lose definition not through destruction, but through a steady softening of its presence in optical and infrared bands. Its halo remains smooth, its brightness remains stable for a time, yet the nucleus becomes harder to isolate. In consecutive frames, the central condensation weakens, then disperses into a uniform glow, as if the object were dissolving into the very light that reveals it. This fading should coincide with a corresponding change in mass, but orbital models continue to hold steady. The trajectory remains coherent, deviating in the same slow, regulated pattern noted earlier. There is no sudden shift, no erratic tumble, no spur of fragments pulling away. Dynamics teams confirm that whatever the visitor has become, its center of motion persists with geometric clarity. Something follows the predicted path even after the visible form becomes ambiguous. Spectral instruments attempt to track the fading nucleus, but their results grow confused. Emission lines associated with the halo's earlier plasma state weaken, replaced by broad, faint features too diffuse to tie to a compact surface. The data suggests that the visitor now behaves as a distributed entity, its defining properties smeared across a larger region than before. It is not an expanding cloud. Its edges remain sharper than any natural disintegration would permit. Instead, it occupies a shape that is neither object nor plume, a coherent presence without a solid center. Spaceborne imagers provide the clearest evidence of this transformation. As they refine their pointing and reprocess their longest exposures, they detect an unusual phenomenon, fine-scale variations in brightness that appear not as jets or arcs, but as soft wave-like modulations threading through the halo. These ripples travel slowly outward and vanish at the boundary of detection. They do not correspond to rotation heating cycles or changes in solar wind conditions. They resemble instead the behavior of a system redistributing its structure from within. Meanwhile, the visitor's influence does not diminish with its fading form. Magnetic murmurs continue to appear across planetary fields, though now more broadly timed and less tied to optical brightness. Communication networks note one last series of synchronized noise dips gentler than before. Timing anomalies retreat into their normal scatter only after the visitor moves well beyond the orbit of Mars. The fading does not mark an end, but a transition. In data centers across the world, the archives tell an unexpected story. As analysts revisit earlier corrupted frames, the missing segments, the blank spectra, the overwritten calibrations, they notice that similar patterns appear in new data as the visitor fades. These are not fresh corruption events. Rather, they occur in the margins of images taken well after the nucleus begins dissolving. Instead of gaps, these new anomalies appear as faint softening of contrast around the regions where the nucleus should be. Not errors, but an absence of distinction, as though instruments attempting to focus on a vanishing target find no boundary to record. Some refer to this phase as the disappearance of the object, but others frame it differently, not disappearance, but migration. For the signals that continue to align, auroral timing drifts, magnetic wavelets, coherent noise smoothing suggest a presence that is no longer confined to a condensed form. The visitor's behavior continues even as its boundaries dissolve. A few researchers attempt to describe the transformation in terms consistent with known physics. They suggest that the nucleus may have fragmented into pieces too fine to resolve individually, forming a cloud of uniform grains that remain gravitationally coherent. Others propose that the halo's plasma sheath has taken on the structural role once played by the solid body, effectively becoming the object. Still others, drawing from plasma cosmology and electromagnetic theory, explore models in which the visitor's identity shifts from matter-based to field-based, with its interactions mediated through charged flows rather than mass. These theories remain cautious and incomplete, yet they share a common thread, the idea that the visitor in this phase exists less as an object and more as a pattern. Its influence continues along its trajectory, and its coherence persists even as its material form becomes indeterminate. The most striking evidence of this shift comes from radio occultation experiments. As the visitor crosses the line of sight between Earth and several distant probes, analysts examine the resulting signal bends. Ordinarily, such events reveal density structures, tiny deviations caused by passing through gas or dust. But in this case, the signals show coordinated deviations without corresponding extinction. Instead of scattering or absorption, the data show phase distortions consistent with a smoothly varying index of refraction 1 that moves precisely along the predicted path. The effect is subtle, like a transparent lens drifting through space. By the time the visitor draws near the orbit of Jupiter on its outward leg, the visible signature has nearly vanished. Only long exposures pushed to the limits of processing reveal the faintest tracing of its halo. Yet the orbital solutions remain confident. The radio distortions continue. The magnetic murmurs taper but do not disappear fully. The pattern persists even as the matter fades, leaving researchers with the impression that the visitor has transitioned from something that occupies space to something that passes through space. In internal discussions, a careful phrase emerges: non-local persistence. It describes a phenomenon that keeps its coherence without keeping its shape, a process that continues even as the object ceases to fit the definition of an object. It is a term chosen for its neutrality, but behind it lies a quiet recognition that the visitor's presence has become something neither fully physical nor fully absent, and so the fading marks not an end but a threshold, a moment when the interstellar visitor steps out of visibility and into a more diffuse mode, leaving behind a path traced not by light, but by the coordinated responses of field signals and timing across the solar system. Long after the visitor's outward glow has thinned into near invisibility, the most active work around it begins not in domes under the night sky, but in rooms lit by screens. With the immediate passage over, observatories release full archives of raw data to shared repositories. What had once moved as real-time urgency now settles into the slow, meticulous work of reanalysis. Teams that were too busy to look backward during the approach now turn their attention to the past. The process begins with routine checks. Analysts at major data centers run consistency tests on stored images, spectra, and magnetometer logs. They look for gaps, compression artifacts, and calibration drifts. The goal is simple: to ensure that nothing critical was missed. Yet as these checks progress, familiar anomalies resurface in a new light. The missing strips in images, the blank lines in spectral files, the softened patches and calibration frames now appear against the fuller backdrop of the visitor's entire timeline. When plotted together, they no longer seem like isolated faults, but elements of a pattern that extends from the heliosphere's edge to the inner system. This realization prompts a broader effort. A consortium of observatories and research institutes agrees to reprocess all data taken not only during the visitor's passage, but also during previous years, when no interstellar bodies were known to be present. The aim is to compare epochs to see whether similar patterns of corruption, timing, drift, and subtle coherence exist in intervals unrelated to the recent event. If they do, then the anomalies may be symptoms of unknown but ordinary behavior. If they do not, then the visitor's passage stands apart. The reprocessing is slow. Massive volumes of archived information must be read, checked, and sometimes reconstructed from older storage formats. Yet, as months pass, a picture begins to emerge. In most years, the rate and distribution of data faults follow expected statistics. Corrupted frames scatter randomly across instruments and targets. Timing corrections show no shared rhythm. Noise floors in communication links wander within known limits without synchronized dips. The systems behave like independent, imperfect machines. By contrast, the period surrounding the visitor's presence reveals a weave of anomalies that is not easily dismissed. In these intervals, missing data blocks in different archives cluster around the same universal times. Timing systems adjust themselves in parallel. Magnetic murmurs at different planets align within narrow windows. Even the soft wave-like modulations in the visitor's fading halo turn out to correspond to small changes in deep space signal coherence. None of these correlations prove a cause. Together, they suggest that something more than chance is at work. Encouraged by these findings, some teams push further back in time. They search for earlier episodes when similar patterns might have appeared unnoticed. They examine years marked only by routine solar activity, scanning for clusters of synchronized timing adjustments and correlated magnetospheric anomalies. For the most part, they find only scattered hints, yet in a few narrow intervals, decades apart, they detect faint echoes, small groups of timing corrections that briefly align across networks, minor magnetic disturbances at multiple planets that do not match solar events, and isolated instances of corrupted data near the edges of surveys. In those intervals, no interstellar visitor had been identified. The sky had seemed empty of such travelers, but the instruments were fewer, the coverage sparser, and the archives less complete. It is possible that similar bodies passed unnoticed, leaving only their faint imprint in the coupling of fields and systems. The evidence is too thin to claim repetition, yet it is suggestive enough to keep the search alive. The process of re-examination transforms the archives into something more than passive storage. They become an active landscape, a place where patterns can emerge long after the original observations ended. In this landscape, the visitor is no longer a single object that approached and departed. It is the central thread in a tapestry of interactions stretching across decades of data collection. From these efforts, a new framing begins to take shape in internal discussions. Rather than speak solely of an interstellar body, some researchers start to describe an interstellar condition. In this view, the visitor serves as the visible anchor for a broader phenomenon that extends into magnetic fields, signal paths, timing systems, and storage architectures. The body is simply the most tangible manifestation of a process that also lives in the relationships among instruments, planets, and the heliosphere itself. This idea remains tentative and carefully stated. Official publications continue to emphasize established mechanisms and to explore natural extremities of composition and outgassing. Yet workshop notes and informal reports increasingly use language that reflects a shift in perspective. The focus moves from what the visitor is made of to how its presence reorganized the behavior of the systems that observed it. In one reanalysis project, a cross-matched timeline is assembled as a kind of silent narrative. It places optical images, thermal maps, magnetometer traces, communication noise plots, and timing logs along a single axis. The result is not a traditional light curve or orbital diagram, but a composite chronicle of responses. When viewed this way, the visitor's story appears less as a narrow spike of interest and more as a broad plateau of altered behavior that spans the entire solar system. This visualization does not answer any questions, but it leaves a lasting impression on those who examine it. They see how small anomalies, trivial in isolation, form a coherent structure when aligned. They see how the visitor's path threads through fields, instruments, and memories, leaving subtle traces at every level. They see how the archives themselves, once assumed to be passive witnesses, now appear as active participants in the phenomenon. As the reanalysis continues, the phrase that began as a quiet suggestion takes on a more defined meaning. The visitor is still studied as an object with mass trajectory and composition. But increasingly it is also described as a catalyst for a mode of behavior, a condition in which the heliosphere, its embedded planets, and their observational systems briefly enter a state of heightened coherence, a state in which matter field and memory align just enough to reveal the outline of something that cannot be fully captured by any single instrument or theory. In this sense, the awakening of the archives is not simply about finding new anomalies. It is about recognizing that the story of the visitor does not end with its departure. It continues in the way the collected data reorganizes understanding in the patterns that become visible only when humanity looks backward with the benefit of hindsight. The phenomenon that once seemed confined to a passing point of light now appears as a broader arrangement written into the long memory of the solar system's instruments. As the reprocessed archives settle into new order, attention turns from the past to the space between explanations. A decade's worth of comet surveys, outgassing models, plasma simulations, and heliospheric studies are brought together for comparison. The results at first appear fragmented, each discipline offering a partial account, each dataset holding a piece of a larger shape. Yet as researchers overlay these fragments, a peculiar consistency emerges. The visitor's anomalies, once tallied as independent puzzles, now arrange themselves into a framework that feels less like coincidence and more like coherence. In reviewing the data, specialists in composition note how the thermal divergence, the warm band, and the cool subsolar zone aligns with the periods of regulated acceleration. The same intervals that showed heat routed along unexpected paths also show motion steered with unusual steadiness. Plasma physicists add that these intervals coincide with the faint ripples detected in the heliospheric current sheet. The correlations are soft, but the timing overlaps with enough precision to draw attention. Magnetospheric scientists point out that the phase shifts in auroral activity across Earth and Jupiter peak just after the brightening event, when the halo entered its stable luminous mode. Meanwhile, communication engineers observe that the largest dips in global noise coherence appear during the fading of the solid nucleus, when the object began to act more like a distributed field than a compact body. These results come from independent groups working with different tools and unaware of each other's timelines, yet the alignments persist. Quietly, a hypothesis begins to circulate, not formalized, not published, but spoken in measured tones at conferences and late-night workshops. It suggests that the visitor's behavior might be understood not merely by cataloging its anomalies, but by treating them as the sequential stages of a system that begins as matter interacts through energy and concludes as pattern. In this framing, the visitor's early phase is dominated by detectable material, a dark nucleus, a smooth halo, a body that reflects and absorbs. During this stage, its presence expresses itself mostly through light and heat. As it approaches the inner system, the second phase emerges a period of interaction. Here, the visitor engages with the heliosphere not forcefully but responsively. Its acceleration smooths, its brightening stabilizes, its thermal profile organizes, and the magnetic murmurs deepen across planetary fields. Finally, as it fades, the third phase reveals itself a distributed persistence in which the visitor interacts less through matter and more through coherence, leaving its imprint across timing systems, plasma flows, and signal pathways. This tri-layered model remains speculative, but it carries an internal symmetry that appeals to those who have spent months following the anomaly threads. It frames the visitor not as an engineered entity nor as a natural accident, but as something orthogonal to both a phenomenon that unfolds through states rather than parts. To test the idea, researchers compare the visitor's behavior against a wide range of natural processes. They review known examples of plasma structures that maintain identity through long distances, such as magnetic flux ropes and detached coronal plasmoids. They study the behavior of self-regulating cometary jets, unusual bodies with metallic cores, and meteoroids that form coherent plasma envelopes during atmospheric entry. Each analogy captures a facet of the visitor's behavior, but none capture the whole. Plasma structures explain the magnetic interactions, but not the stable light. Metallic cores explain the thermal conduction, but not the absence of a tail. Sublimating jets explain the non-gravitational acceleration, but not the regulated drift. In contrast, when the behavior is viewed as a multi-phase continuum, the pieces begin to fit. The visitor's early solidity complements the mid-stage electromagnetic response, which in turn foreshadows the late-phase non-local persistence. Each stage transitions smoothly into the next with no abrupt discontinuities. The phenomenon behaves like something that adapts to its environment, not through intention but through underlying principles that respond to field heat and motion. Philosophers of science enter the discussion offering a broader interpretation. They suggest that the visitor challenges not the laws of physics but the assumptions built around categories object field signal. The visitor might simply occupy a region of parameter space, rarely encountered a boundary where matter behaves like field, and where field adopts properties typically assigned to pattern. In that boundary, rigid definitions falter, and new modes of explanation become necessary. This perspective influences how scientists draft their internal documents. Instead of describing the visitor as anomalous, some begin to describe its behavior as emergent. Instead of listing irregularities, they identify consistencies across domains. Instead of asking what the visitor is, they ask what conditions it expresses. A new phrase gains quiet traction: autonomous coupling. It denotes a system that interacts with its environment through self-consistent responses without requiring control or intention. Applied here, it suggests that the visitor's behavior's regulated accelerations synchronized, brightening coherent magnetic effects might arise from a single underlying property, one that allows the system to maintain identity across different physical regimes. Even with this language, the phenomenon remains only partly understood. The visitor's path, though now deeply studied, offers no final revelation. Its behavior is neither fully natural nor definitively artificial. It sits at the threshold where physics meets structure, where reaction meets regulation, and where presence becomes condition. In this emerging view, the visitor becomes something quieter than mystery and more grounded than speculation. It becomes an event of coherence, a system revealing that the boundary between object and environment is thinner and more permeable than once assumed. A system showing that identity can persist without shape and that influence can unfold without force. By the time this framing settles into the background discourse, the visitor is already far into the dark beyond Mars, its faint imprint stretching behind it like a softening echo. Yet its impact grows sharper in the minds of those who trace its path. For the first time, they see not only what the visitor did, but how the solar system behaved in response. And from that understanding begins the next step to question whether the visitor altered the heliosphere or whether the heliosphere revealed something about itself in the presence of the visitor. Years pass after the visitor's faint halo slips beyond the reach of even the deepest exposures. New surveys begin, new missions launch, and new objects are catalogued along the endless lanes of the sky. Yet within models' archives and quiet conversations, the presence of the interstellar traveler does not fade. Instead, it settles into a different form, less like an event remembered and more like a condition that can reappear whenever certain patterns align. In dynamics laboratories, the equations that once treated small non-gravitational forces as noise now accommodate the possibility of long-regulated accelerations. Analysts refine their tools, building fitting routines that can distinguish between chaotic outgassing and coherent low-intensity thrust. These routines are applied to old comet data and to newly discovered bodies. Most show only the expected scatter of natural behavior, but a few reveal hints of smoother curves, faint suggestions that the visitor was not entirely alone in its mode of motion. Each candidate becomes a subject of careful scrutiny, not as proof of repetition, but as a test of the broadened framework the visitor has inspired. In heliophysics groups, models of the heliospheric current sheet and planetary magnetospheres now include terms for subtle, distributed perturbations patterns that travel ahead of moving structures rather than trailing behind them. The ripples once seen during the visitor's passage become templates for possible field-level responses to traversing systems. These templates are used to interpret new data from deep space probes and planetary orbiters. Most of the time the fields behave as they always have, restless, complex, and mostly governed by the sun. Yet occasionally small sequences of coherent variation appear, and when they do, researchers ask whether the solar system is briefly entering a state similar to the one that accompanied the interstellar traveler. Communication and timing specialists also carry forward quiet lessons. Diagnostic systems that once flagged only large deviations now track the tiny synchronized adjustments that emerged during the visitor's presence. Global networks of clocks, relay satellites, and deep space antennas are monitored not only for faults, but for episodes of subtle convergence. When noise floors dip together, or when corrections cluster more tightly than expected, the events are catalogued with reference to a growing library of patterns. The aim is not to assign each anomaly to a cause, but to recognize when the infrastructure itself moves into a more coherent mode. Within data archives, the notion of passive storage gives way to a view of living memory. The gaps, softenings, and correlated errors that once seemed like inconveniences are now treated as signals in their own right. Automated tools scan for clusters of missing or homogenized data, mapping them against celestial events, planetary configurations, and heliospheric conditions. Most clusters resolve into mundane explanations, maintenance windows, software updates, hardware aging. Yet some remain unassigned, sitting at the edges of understanding, echoing patterns first traced during the visitor's journey. Theoretical groups attempt to synthesize these threads into a general framework. Some explore the mathematics of systems that maintain identity by coupling to their environment, borrowing concepts from complex networks and self-organizing media. They study how patterns can persist in fields, flows, and information streams without relying on rigid structures. In such models, the visitor appears as one instance of a more general possibility, a system that expresses itself through coordinated responses in matter, magnetism, and memory. Whether such a system arises from natural extremity or from an origin beyond current categories remains an open question. Philosophers of science and methodologists engage with these developments from a different angle. They note how the visitor forced a shift from object-centric thinking to condition-centric thinking. Instead of asking only what a body is made of, researchers now ask how its presence reorganizes everything around it. This change in perspective affects not only the interpretation of the interstellar traveler, but also the way other phenomena are approached. Sudden brightenings, unexplained timing, drifts, and coherent field changes are no longer dismissed solely as instrumental complications. They are examined as potential manifestations of transient states in which the system of observation itself participates. Despite this broadening of view, caution remains. Official language stays restrained, emphasizing natural mechanisms, incomplete modeling, and the need for more data. No formal consensus emerges that the visitor was anything more than an extraordinary member of a vast population of wandering bodies. Yet beneath the careful wording there is a shared awareness that something changed. The solar system, once seen as a stage on which objects pass and instruments record, now appears as a layered medium capable of hosting episodes of extended coherence. In classrooms and outreach lectures, the story of the interstellar traveler is told in simple terms. A dark object came from the space between stars, behaved in ways that did not fully match expectations, and left behind questions about how matter fields and information intertwine. For many, that is enough a narrative of wonder and humility, a reminder that the universe is still capable of surprises. For others, especially those who work with the data, the story runs deeper. It carries the sense that the visitor revealed not only something about itself, but also something about the networks and environments through which it passed. In the end, no single interpretation prevails. Some view the visitor as a natural outlier, a rare combination of composition and history that produced a cascade of unusual effects. Others consider the possibility of emergent behavior, a system that arises spontaneously when particular thresholds in plasma magnetism and structure are crossed. A few allow themselves to wonder whether the phenomenon might reflect a form of autonomy, a way for patterns to preserve themselves across the emptiness between stars. What does endure is the idea that ATLAST, as some came to call it, has become more than a distant traveler whose orbit is now a line in a catalog. It has become a reference state, a condition the solar system may enter when the right combinations of body field and infrastructure align. In that state, small anomalies align into quiet structure, instruments slip into subtle synchrony, and the boundaries between object and environment grow thin. Somewhere in future years, another interstellar visitor may cross the heliosphere, or perhaps none will, and the patterns traced by this one will remain singular. Either way, the memory of its passage stays embedded in models, in archives, and in the instruments that now look outward with a slightly different expectation. Not of spectacle or certainty, but of the possibility that at any time the ordinary fabric of measurement might briefly reveal an underlying coherence, a coherence that does not shout but whispers through fields and systems, inviting recognition without demanding conclusion.